straight lines. We start with the most basic of the function, which is the lines. This thing you see here is GeoGebra. It's a computer tool that you will use in the course. Don't worry about the left part, look at the right part where the graphs are. And we start with a very basic line. Here, for example, with the y equals to 2x. This is a function, and its graph is a line that goes to the 0, 0, and it goes, as we grow in x, it grows in y. Now, for example, we have another line, 2x plus 5 is parallel, 2x minus 6 is parallel to this one. Actually, we can put a slider here to see a bunch of lines parallel to y equals to 2x. And you can see as we move the slider, how the lines move. Observe the equation on top. Don't look only at the graph, look also at the equation, as the equation moves. What happens if we change the number? Instead of adding, we multiply by a number different from 2. That's called the slope, and the line will become more or less vertical. For example, if we start with a negative slope, we get this line, and as the slope becomes more positive, the line, or less negative, the line becomes horizontal till it starts going into the direction. What about the lines that go through one point? For example, the point 3, 2. Okay, if we want to write this line, what we have to do is we start with the line y equals to 5x. Here, this is the line y equals to 5x. And then we first move it, so the 3 goes to the 0. It's parallel, the slope is the same, and now we have to push it upwards, for which we add plus 2. Parabolas. Our next set of functions are quadratic polynomials whose graphs are parabolas. That's it, polynomials of degree 2. We start with something very simple, like y equals to x squared. You can see the point 2 goes to 4, and let me zoom here a little bit, or move it rather, so we see also the point minus 2 goes to 4. The image of 2 and the image of minus 2 are 4, and that's allowed for a function, two different points to have the same image. What is not allowed is to have a point with two different images. That's not a function. What happens if we multiply the number here? Instead of y equals x squared, we multiply by a number. For example, the 0 is this, and multiply by 0.5 here. You see the parabola is more open. This is y equals 0.5x squared compared to y equals x squared. Now, as the number grows, parabola closes and closes, becomes narrower. Here in red, y equals y squared, and this one, it becomes narrower. Very, very close as the number grows. What about the other factors in the polynomial? For example, if we add a linear factor, y squared minus 4x, we find the parabola has been moved and displaced somewhere. The 0, 0 becomes now 2 minus 4. And now if we add 9, the parabola goes up. This we know already, that adding a number on the y variable makes the parabola move vertically. This parabola is the same as y equals this expression you see here. That's called completion of squares. Both parabolas are the same. It's simply a different way to express it. Exponentials and logs. The next function we're looking at are the exponentials, which are used in the modeling of population. E to the x, this function, grows very fast to infinity when x is positive. See, if we zoom out, you can see at 5 the function already takes the value something like 40. In the same way, it goes very fast to 0 when the variable takes negative value at -5 here. If we zoom in, the function e to the -5, or rather the value e to the -5, it's almost 0. This function, as I said, is used for the modeling of virus, for example. You may have seen it in the newspaper. The function has an inverse, which is the log, natural log, that you must have seen in high school. As we know, the graph of a function and its inverse are symmetric with respect to the line y equals to x. Here you have the line y equals to x, and it's natural that these two functions are symmetric because here y is a function of x, and here we interchange the roles, and x is a function of y. You just interchange x and y, so they have to be symmetric. The base can be changed. It's not the only exponential we have. For example, we could take, instead of e to the x, we can take 2 to the x. 2 is a little bit less than e, so e grows is slower than e to the x. We can take 5 to the x, it grows faster. And all these functions, of course, comes with their correspondence inverses. Here, 2 to the x has inverse the log base 2, and 5 to the x has inverse the log base 5. You can also take a base is less than 1. For example, 0.5 to the x. If this green one is e to the x, we have 0.5 to the x. It becomes like sort of symmetric with respect to the y-axis. Not exactly symmetric, but let's say to the other side of the y-axis. This is e to the x in green. This is 0.5 to the x in yellow, amber. Of course, we have an inverse, is the log of base 0.5, and sorry, here it is. And these are funny because the function 0.5 to the x and its inverse log base 0.5 intersect at a point, which didn't happen with the exponential and the natural log. Trigonometric functions. The trigonometric functions we start with is the sine of x. Here is the graph of the sine of x. Can be used for things that repeat. For example, sales of ice creams. You can see the top is the sale in the summer. As the weather gets colder, the sales go down. In the winter, it's down. Here you have a smaller number of cells, and again, as the weather becomes warmer, the cells increase. So that's a periodic thing, and that's something you can use to model the sine function. Here is the cosine function. As you can see, the cosine and the sine function have similar graphs, except one is displaced with respect to the other. If we want to move the graph of the cosine to make it coincide with the graph of the sine, what we need to do is change in the independent variable, add a number in the independent variable. See, if we move to the right, there, you look at the left, is cosine of x minus 1.547, that's pi over 2. So we have here that the cosine of x minus pi over 2 is equal to sine of x. These two functions are the same. And you have thus your first trigonometric identity. Sine x equals cosine of x minus pi over 2. Let me put back the cosine to what is normal cosine x, because we need it for some other things. Okay, so we'll erase here on the left this 1.547 or 69 to have the cosine of x. Okay, other function we have besides sine and cosine is the tangent. The tangent is the quotient of sine divided by cosine. As you can see, the tangent is not defined. Sorry, we have also the reciprocal of this. For example, the sine has reciprocal secant, 1 over the sine. Here, where the sine is 1, 1 over 1 is 1, so the cosecant, sorry, this is a mess. Other trigonometric functions, for example, the tangent, which is the quotient of sine over cosine. Here is the graph of the tangent. And we have the reciprocals of this one. For example, If we consider now the sine of x as before, let it erase this and put the sine of x. It's reciprocal. 1 over the sine of x is called the cosecant. It's the blue one. You see when the sine is 1, 1 over 1 is 1, so the cosecant is also equals to 1. And that's where these two graphs intersect. When the sine is 0, 1 over the sine cannot be defined, right? And that's why the cosecant is missing a lot of points. You can see, making this smaller, you can see how the cosecant is not defined whenever the sine is equals to 0. For the cosine, we have its reciprocal, which is the secant, with the same type of property, not defined in many points. Let's see how the graph looks like. Here it is, also in green. And similarly for the tangent. The tangent already is missing many points because whenever the cosine is 0, you cannot divide by 0, so there is no tangent there. But here, well, okay, sorry. But here we have the cotangent, 1 over the tangent. Nice, right?